Hello everyone. So today I will talk about LIMRs and their effect on non-linear structure formation. To begin with, so this is the density plots of various components of the universe. So as we know that today the universe is dark energy dominated, but at earlier time it was radiation dominated, and at that time neutrinos were occupying a major fraction of that total radiation, and hence playing a major role in governing the dynamics of the universe. And even today at late times, the density of the neutrinos is though very less, but it has very unique signatures on the structure formation, and that we will talk in the next few minutes. Yeah. So to go through with some basic neutrino properties. So as we know that neutrinos are massive and they follow the Fermi-Dirac distribution with a temperature that is less than the photon background temperature. And depending on their mass, they can be either relativistic and they can be might be non-relativistic. And the one special property about neutrinos that even if they have become non-relativistic, they still have very high velocities. And if from this you can see 0.1 electron volt mass neutrino will have a velocity order of 1000 kilometers per second, and this is very high velocity that cannot be neglected in terms of structure formation and etc. So corresponding to this velocity, we can associate a length scale. So significance of this length scale is that below this length scale, the neutrino will free stream and they will oppose the structure formation. And above this length scale, they will behave like as a general dark matter or the standard dark matter. Yeah, so to see the cosmological effect, especially in the context of linear cosmology, the effect can be parameterized in terms of three parameters, which is its contribution to the relativistic energy density, that is parameterized by delta N effective, its contribution to the current energy density, and its free streaming. And you can see by the definition they are nothing but the movements of the phase space distribution: first movement, second movement, third movement. Ideally, in principle, one expect that it will go to it should depend on nth movements, higher movements also, but given the precision of current cosmological observation, these three parameters are enough. And among these three also, only two independent parameters are there. So in context of linear cosmology, the effect of neutrino-like species can be parameterized only by two free parameters: the N effective and MS effective. So today I will not talk about the standard neutrino stuff, rather than I will talk about the non-thermal neutrinos. So this is how there is a comparison between non-thermal and the thermal one. So the red one is the non-thermal neutrino distribution. You can see that both the plots, they correspond to the same delta N effective and same MS effective, and they look very different. And you can see that the standard, the Fermi-Dirac one, it is localized at a low momentum. However, the non-thermal one have a non-vanishing tail at higher momentum side, and this will have some interesting signatures in the cosmology. Why we are talking about the non-thermal neutrinos? Why not the thermal one? So the primary motivation behind the non-thermal sterile species was the Asset tension. So Asset is a parameter, is a combination of two parameters, sigma 8 and omega m. And sigma 8 is it gives the information about the clustering of the matter. So the Planck measurement of this Asset parameter using a lambda CDM model, this gives a slightly higher value of Asset. On the other hand, the weak lensing surveys, they give a low Asset parameter. They infer a lower Asset value. So there might be a discrepancy, or there might be a presence of the new species we are missing in the lambda CDM model. That's why we are getting a slightly higher Asset in the lambda CDM model. So that's why we are thinking that there might be presence of a non-thermal sterile neutrino. So the other question comes in our mind, that why not a thermal one? So a fully thermalized fourth species will contribute to N effective to 1, and that is not allowed by earlier cosmological probes like BBN or even the Planck. They are consistent with the N effective is equal to 3. They can accommodate a new fully thermalized species. In this non-thermal model, we have freedom because it contributes to delta N effective very less. It is contribution of this non-thermal species is coming to be nearly 0.03 order of 0.05 maximum. So why it shows the acid tension? So this is the residual of the matter power spectrum with respect to the lambda CDM. And you see there are two kind of plots, the blue one and the red one. So red one is the corresponding to the standard model, and the blue one is the corresponding to the non-thermal. So you see there is a high suppression on the high K side, or the small scale, there is a suppression in the matter power spectrum, and that's what it solves the acid tension, because it is suppress the, I mean, there is a suppression, it means it suppresses the growth of the perturbation, and that's what is solving the acid. In you see that in the red also there is a suppression, but that suppression is not enough to solve the acid tension fully. So the standard neutrinos are on the right track only. They reduce the acid tension, but not fully solving the acid tension. On the other hand, this model is solving the acid tension. So we have taken for our study, we have considered the other well-known non-thermal models, which are the Dodelson-Whitbread and the Gaussian one. All three, they are correspond to the same MS effective and same delta N effective. And if they look very different, their cosmological signature should be also very different, right? So what we found in linear cosmology, this is the residuals of the CMB power spectrum. In linear cosmology, that is blind to all other properties, because in linear cosmology, the signature, they overlap to each other. So we cannot distinguish among the all three non-thermal models. And this also sets a motivation to do a non-linear analysis to distinguish among these all three non-thermal models. So to do the non-thermal n-body simulation, we have used the gadget code, and we have used a 1 gigaparsec box size. So I will skip the details here. So the initial condition of the n-body simulation, they are set by the linear matter power spectrum and the linear growth rate. Okay, so in CDM, they are completely set by the power spectrum and the growth rate. But in LIMR component, apart from the gravitational peculiarity, they have very high thermal velocity as well. So there are various methods to set this velocity assignment. So we are using this particular method to do the assignment of the velocity to LIMRs. So coming to the results, so these are the density contrast of the two components, the CDM plus barium component and non-thermal LIMR component. So in non-thermal LIMR component, the structures are more smeared out, or it means the less prominent over densities and less prominent voids. And this is because of the free streaming of the non-thermal neutrinos or non-thermal stellar neutrinos. Coming to the matter power spectrum, so there is a maroon color, that is a linear prediction of the matter power spectrum, and this one is the output of the n-body simulation. So you see that this is already the linear prediction, it is already different from the linear prediction, because this is a better treatment of the predicting the matter power spectrum in the non-linear regime of the cosmology. The other other comparison you see with this green one, that is a match sigma 8. So this is a lambda CDM model, but the sigma 8 of this lambda CDM model is matched to the non-thermal model. So the comparison why I am showing this is because in case of standard neutrinos, these both the signals they are degenerate. It means the effect of neutrino mass is captured by the matching the sigma 8 condition, but that is not the case in the non-thermal neutrino. So to understand the non-linear evolution of the halo, so properties of this this density profile is very important. The one such property is the mass concentration relation, and you see the concentration in case of the non-thermal LIMR, they are suppressed over this mass range, and that suppression is nearly monotonic suppression. And in this signal also the effect is not matched by the match sigma 8. That is also contradictory from the standard neutrino case. So why there is a suppression? This can be understood from the power spectrum itself, because at a small scale there is a suppression. Yes, so there is a suppression in the matter power spectrum, and this in fact delays the onset nonlinear evolution, and that's why there will be less structures, and if there will be less background density, it means the less concentration will be there. The other thing we went for the weak lensing signals, that is weak lensing signal is proportional to the excess surface mass density, and we see that there are error bars, they are shown with they are the error bars from the photometric surveys, and we see that in non-thermal case the signal is already out from the error bars, and in future experiments the error bars will shrink more, and this will be, I think this will be ruled out in the future photometric surveys. Another important result is that whatever all the three models, the Dodelson, Withrow, Gaussian, and the non-thermal model, they were same in context of linear cosmology. Linear cosmology was unable to see them different, but in non-linear signatures we found out that non-linear cosmology they have different signatures, and it means we can distinguish among all three non-thermal models, and these are my conclusions. Yeah, and I would like to thank my collaborators.
Time for a couple of short questions.
Hi, so thanks for the nice talk. I have a question. So you can probably do the same thing with sterile neutrinos, right?
Yeah, that's what we did on.
It was actually. Okay, yeah. Yes. No, but okay. Technically, what I'm maybe what I was trying to ask is, suppose you use different models, right? So there's the Schieffuller model. Dodelson-Withrow actually, if you look at the X-ray constraints, are actually ruled out. So that's why I didn't sort of catch my mind. But Schieffuller is, I think, probably still allowed as a dark matter candidate. Will it have some effect? You know,
I'm not completely aware of this Schieffuller, but is it in the hot? So our argument is that any hot like that comes in the hot thermal dark matter, I mean in the category of whole thermal dark matter, that will have I think that will have the same similar I think similar pattern, that will follow the similar pattern.
Okay, one last quick question.
So so just to understand the cluster constraint, so so essentially you have a suppression of the delta sigma throughout the cluster's profile. Is that right?
Yeah.
Okay, but like you can in principle already start putting constraints, because there are comparisons with CDM of the cluster profile and how consistent they are with CDM. So in principle, you could try to actually get a constraint on the model as well.
Yes.
Right. Yeah. Have you tried something like that?
I think we have not tried. So yeah.
Okay.
Okay, let's thank Ravi again.